Hello, today we're going to discuss about Runge-Kutta method. So earlier on, we recall Euler method that you have learned before. Now this Euler method is denoted by yn equals to yn minus 1 plus h f of xn minus 1 yn minus 1. Now this is Euler method. This Euler method compute f only once in each step. But Runge-Kutta method, on the other hand, compute f 2 or more times. Okay, and this gives greater accuracy and better stability if compared to the Euler method. The idea of Runge-Kutta method is done 100 years ago by Runge and Kutta, where they constructed different types of method, and both of them are shown to have greater accuracy. So Runge-Kutta method is denoted by sometimes I will write at RK. Okay, so we have y, big Y, yn minus 1 plus h summation j equals to 1 to s aij f of xn minus 1 plus cj h yj, where I takes from 1 to s, and then we have the little y, given as yn minus 1 plus h summation r equals to 1 to s bi f of xn minus 1 plus cih yi. Now I would like to explain all these terms used here. So this is a one-step method where my yi denoted as the internal stage. My yn here is the update. Okay, you know these are the constant. The initial value yn minus 1. Okay, and we have the a's. This a is the matrix A of this function. This can be written as a Boucher tabular given by A, C, B transpose. Okay, so, and we have the C condition, the row sum condition, where this C is the summation of aij. Okay, where my I start from 1 to s. My s here is denoted the stage. Okay, so we can see that the C here, or even this C, this is the vector of abscissas, and this A is the matrix of coefficient. So it's all contain numbers here. Okay, and this B is the quadrature rate. So this B indicate how the approximation to the solution depends on the derivative of these internal stages. Okay, Runge-Kutta method can be divided into two. Okay, we have if A is lower triangular, then you have explicit method. On the other hand, if A is full matrix, okay, we have implicit method. Okay, so there are also semi-implicit method or diagonally implicit or singly implicit. So we just want to focus on explicit method. Explicit method is very easy to be implemented. Okay, let's focus on explicit method. So why explicit method is easy to be implemented? Because the internal stage calculated directly. The internal stage my yi calculated directly without depending on the latest digit. This method also said as a cheaper implementation compared to the implicit method. Okay, one example of explicit method is the Euler method, which can be given as the Boucher tabular as this 0, 0, 1. Now we can say that as you know earlier on, this is my C, these are my A, this is my B transpose. So I can write the Boucher tabular for this, like it's only have one yn minus 1. Okay, and we know that the function Euler method is given by yn minus 1 plus h f of xn minus 1 yn minus 1. This is the Euler method. Let's say y1, not y1, it's y. Okay, big y plus yn minus 1 is my big y. Okay, so this is the Euler method. So the update depends on my b here, the weight, quadrature weight, which is 1 here, so there is no the value is 1. Now another example of explicit method is the midpoint rule. Now the midpoint rule is given as, the Boucher tabular is given as this 0, 0, 0, 0, 0, 1. Okay, as I can say, there are two stages here. So I have y1, y2. These values here are my c's. Okay, and this value here, these are my a's, and this is my b transpose. So if you look at the standard explanation earlier on, okay, the Runge-Kutta method, the internal stages, you have your A coefficient or matrix here, together with the derivative f. For the little y, you have this b, together with the derivative. So to write this derivatives form, we have, okay, so this can be written as y1 equals to yn minus 1, because there's no a here, Remember, for the first stage, internal stage, A is a summation of your coefficient here. Now for y2, we have y2, I have yn minus 1 plus h over 2 because of the half here, f1. Now what is f1? My f1 is f of xn minus 1 y1, and my f2 will be f of xn minus 1 plus h over 2 y2. Okay, which is good. Now look at the little y, my little y, yn. Now I have to refer to this one. So I have yn minus 1 plus, obviously, h, my b is 0, f1 plus h, my b is 1, f2. So I can write this one here, hf2. Okay, you can always substitute your f value here, so that this gives, my f2 is f of xn minus 1 plus half y2. So this is the midpoint rule. Now let's look at trapezoidal rule. Where the picture tableau is given as half and half. So one thing I didn't say, if you recall the row sum condition for my C. Okay, C, J equals to summation from J equals to 1 to S Aij. Okay, this is the row sum. So this C here must be the summation of A. This C here must be the summation of A. It's very important to take note of that. Okay, how do you write this? Okay, we have y1, yn minus 1 because there's no A here. Now f1 will be f of xn minus 1. My C is 0 here, so just yn minus 1, which I can also write as y1. Now y2 will be yn minus 1 plus A is 1. So we have h f1 plus 0 here, hf2. Okay, now this will give me as this one. Now f2 equals to yn, f2 is the function for my f of xn minus 1, I have C here, plus ch y2. Okay, so, sorry, my C is 1. My C is 1. ch C is 1, and this is y2. So therefore my little y is given as yn minus 1 plus half h over 2 f1 plus h over 2 f2. And you can put the values of f1 and f2 here, or leave it like that. Okay, now this is our trapezoidal rule midpoint and Euler method. In our next class or next session, I will introduce you to arcade method with more than 2 stages. That's all for today.